So that's a little teeny taste in a few directions. There's one other thing that I want to draw your attention to, and then you sort of have all the tools that are easy to, or nominally easy to explain. But actually, first I'll pause. Is everyone okay with this? Like really, honestly, okay. Please ask me questions now. Yeah? Okay. So we can actually we can do things with more than one piece of audio data, right? Okay. So audio op. If we go back to the docs that actually are filled in with text. Audio op up here, there's a function called add. Here it is. Add fragment 1, fragment 2, and then that bit depth, right? So if I have, so I still in my interpreter I haven't lost that noise data. I just copied it, right? So I still have up here the original noise data. It's right here. It's called audio data, right? So if I open another file, I have a second file. It's called 440 sine. You can all guess what it contains. It contains 5 seconds of a mostly pure sine tone, so I'll make this quiet. Yeah? Delicious. Sine tone. Okay, so if we can read that in the exact same way, so we'll say second reader equals wave dot open. Okay, so now that reader, in the same way that we did with the first wave file, it's pointing at that file. It's opened it up. So if I didn't know for a fact that all the statistics or all the properties of this wave file were the same as the first one, I'd want to investigate them and make sure that the sample rate and the number of channels and the bit depth are the same and store them somewhere. For now, we're going to assume that because I know this is truth. So these two things. So we're not going to worry about those properties again. But they're there and they should be investigated. So we can grab a second of that sine wave, the same way that we grabbed a second of the noise. So we'll do and then we'll get a second, which is 44,100 samples. Okay, so now again, some sign has data in it, just in case you don't believe me. Right, there's data. Okay, so now we have some sine tone and some noise. So using that audio op, using a different function called add. An add takes 2 pieces of audio data. Now these functions are fragile. So things will happen that you don't expect and can't control if those 2 pieces of audio data don't have the exact same properties in every way you can possibly think. So if the pieces of audio data are not the same length, the same sample rate, the same number of channels, and the same sample width, something fun and exciting that you probably don't have control over will happen. I do not recommend it. If you want to do something where those are the starting parameters, you should be using different libraries. So with that caveat in mind, so we know we have a second of the sine tone and a second of the noise, and they're the same property-wise. Yeah?
The question marks instead of actual data. Do you have
Oh, the question marks are okay. So remember how I said it was scary string data? So some scary string data can't actually be displayed in the terminal. It's like Chinese characters or some Greek or something that your terminal doesn't know how to display. So it's larger than the Latin 1 character set. It's not
we'll
really
discuss it
later. It's not really and move on. Yeah, it's not really string data. It's other data pretending to be strings. Yeah. Move on.
The version is too far away from audio.
Yeah. So the answer is it's still fine. Question marks are okay. We'll just press up.
Come back.
Yeah. So if we're adding, so we have, what did I call that? I called that, I can't remember my variable names. Quiet noise. It's right there. So quiet noise, and the one we just grabbed, which is called sum. It's up here, sum sine. Sum sine. And I believe I have to tell it the width as well, don't I? Yes, width. Okay, so then the width is 2. So now this one, complex bits, has the addition of quiet noise and some sine. Okay, so small pop quiz. Does anyone in the audience know enough about audio to tell me why I don't just want to write that to a wave? So I've just added this signal and this signal together to a big signal that has both of them. Does anyone know what bad will happen? It has nothing to do with Python. Huh? It will clip. Very good. So do you know, without thinking about Python at all, how do I solve that problem? I have two waves. Now I have one wave that's more powerful than the two separately. Was the answer divide? I hope it was. By the number of signals? Right. So remember earlier when we just made the quiet noise, we multiplied by 0.5, right? So we want to do the same thing with this one because we've added two waves together, so we have to divide by 2 so that the total is the same as what we started, right? We're taking the average, but we're taking the average in steps. So really what we want is, we'll call this. It does work because what it's doing under the hood really quickly is sensible. The issue is just that you can't sort of get at all the pieces in a way that makes any sense above. So because it's actually doing it all as 32-bit floats is the quick answer. You can't see it. There's a lot of C code that is wrapped lightly. So we say normed complex bits. Okay, so now we can write this to another writer, and then we'll have the two together. So, and in fact, I'm just going to use the same one I used before, because everything will be the same, except we'll have something different in it. With a different name, though. So again, we have to set those properties. So the frame rate is 44.1, the number of channels is 2, and the width is 2. Right, same as before. And then we write the data, which will look like writer dot write frames. And here we will stick our data, which is called normed complex bits, this one. And that's it. Okay, so now we close it up. And then if we go and we play it, we should have a sine wave mixed with a noise. Right? So you hear noise, sine. Yeah? Okay, so the only other thing that you should sort of think about is that it's possible to be a sequencer, the most painfully ridiculous sequencer ever, using this. So if I open that writer back up again, so I have no more data, I'm going to call this sequence. And then I'll set all the properties again. Okay, so frame rate, channels, width, again. So if instead of just writing the one thing that I made, okay, these are strings. If I add two strings together in Python, what happens to the result? So if I have a word hello and a word world, and I do hello plus world, what's the result string? It's hello world, right? Okay, so now, with great power comes great responsibility. So if I do the following, if I say some sine, remember that's our sine tone, and then I say plus quiet noise. What's going to happen? Does anyone want to venture a guess? So what would the audio file look like if I write that sine tone for a second and then the note? Yeah, that's right. So if I write this and then I close it and I go look at what happened. So we have sequence. And it's 2 seconds long. See over here? The OS knows it's 2 seconds long. If I play it, I get sine tone and some noise. Okay? So those are all the tools you need to make the most ridiculous sequencer out of sampled tones that you can possibly imagine. So I think we'll